All right, AP Chem Squad. In this video, we're going to talk about net ionic equations.
So we are going to take an ionic compound lead nitrate, and I'm going to take a little bit of sodium iodide. If I take this light bulb and I put it over here, is anything going to happen? Right? It is not lighting up. Why not? Because it's an ionic compound. Are there any free flowing electrons in there? No. But now, if I take some water and I put it in water, right? Water is not lighting up. Correct? Why not? Who can tell me why is water not lighting up? Because it's a molecular compound. Molecular compounds do not form ions, they stay as molecules. All right? So that's very important understanding. That means you're not going to disassociate them. And now, if I take this water and I put it in, I'm going to take out some. If I take a little bit of this solid and I put this here, and I put a little bit of this solid and I put it over here, okay, and I'm going to add some water. Now if I added some water here, should it light up now? Yes, that same water that was not lighting up, because now what did the water do? It pulled those ions and it is able to light up. Same thing will happen over here. You are able to light that up. Correct? So now what has happened, this ionic compound that was not able to light up here as solid is now changed into ions. And now if I am going to take this and I am going to take this and I mix it, what happened? I got a precipitate. Now this is what is happening at a macroscopic level. What is net ionic equation? What you are seeing at this macroscopic level, but we have to try to understand what is really happening at a microscopic level. Okay, if I'm going to put this over here, is this still going to light up? But did you guys see how it is lighting up a lot less as per compared to the other one? But the light in hydrochloric acid is much brighter compared to the acetic acid. So we'll talk about, can somebody tell me why hydrochloric acid is? It's a strong acid. We had sodium iodide and lead nitrate, right? So its molecular equation is going to be what? You're going to write down PbNO3 2 is reacting with, I took sodium iodide, is reacting, and what type of a reaction is this, everyone? Double replacement reaction, right? So I will get the product as PbI2 and NaNO3. Everybody clear? So this is called your molecular equation. That is what you were doing till now. That is exactly at a macroscopic level. But do we agree, is this staying like this? Now when I added water, that means what did I change this to? If I gave this phase as a solid, will you convert it into ions? No, because we saw when it was in a solid state over here, it was not conducting. But if I dissolved it in water, now instead of solid, I write this phase as AQ. What does that mean? It means that this is not going to stay bonded to it. It is going to change into Pb plus 2. And because you have 2 over here, it is going to be 2NO3 minus 1. Agree? And then over here, the same thing. If this is aqueous and not solid, because I added water, you're going to disassociate that. If it was solid, you would not disassociate it. We need to know the charge, where I'm getting the charges, by looking at the periodic table. Now, based on our solubility rule, we know this was aqueous. Now we are looking at this. When you saw this, you can very clearly see there is a solid at the bottom and there is something that is aqueous on the top. Now, how do we know? That is where our solubility rules come in play. So, based on solubility rules, we know what happens. The lead compounds, the halides of lead, and which are the other ones that you need to know? Silver and mercury. These halides will always form a precipitate. What does it mean that it's going to form a precipitate? That the phase of this one is going to be solid. What you need to know about the nitrates, this is another solubility rule that everybody needs to remember, that all the nitrates are always soluble. And if this is insoluble, what that means? Insoluble is telling you the phase is solid, this one is aqueous. Now because it is solid, are we going to disassociate that? No, I'm going to let that stay as PBI 2, and then this one, because it is aqueous, I'm going to disassociate them into ions. Right? That means they can tell you which one is your precipitate. You should be able to identify this is one is the precipitate which was in yellow color. So before you do that, this is 2. So I'm going to write down 2 NaNO3 over here, 2 over here. So as a result of that, I would have 2 Na plus, 2 I minus, and I would have 2 Na plus and 2 NO3 minus. Now if you're looking at this and you are seeing that I have NO3 over here and I have NO3 over here. So what do we call these? These will cancel out and we call them spectator ions. So these are your spectator ions. So do you guys see, this is called your complete ionic equation. But now when we get rid of the spectator ions, which in this case this and sodium, they are the same on both the sides. That means they are the same in the reactant and they're same in the product. They are both your spectator ions. So now what will be my net ionic equation? My net ionic equation is going to be Pb plus 2 plus 2I minus is giving me PbI2. Now AP does not care if you do not write down the phases, if this is asked. But if they are giving you the phases, you should be able to understand what does that phase imply and what you're going to do with it. Sense? So molecular equation, complete ionic equation, and your net ionic equation. In our AP courses, a lot of time you will see problems where they will only give you the net ionic equation. They will get rid of all these spectator ions. And you should be able to understand if they said a sodium salt was reacting and then you are working, where is this sodium salt? You need to understand that that sodium salt was your spectator ion and it is, have we really got rid of it? Is it still present in my solution over here with the precipitate? Yes, but it is not important because it is staying as the. One more example, let's say if I gave you H3PO4 reacts with magnesium. What type of a reaction is this? Single replacement reaction, right? So my product over here is going to be MgPO4. This is 3, this is 2. And what is a gas that is always produced when a metal reacts with an acid? Hydrogen gas. Agree? We call this as a gas forming reaction and also a single replacement reaction. This is your gas forming reaction because this is a gas. What is the phase of acids always? Acids are always aqueous. What is the phase of magnesium? Solid. It's a metal. Now let's say if I told you to write down the net ionic equation. If you look at this, how many of you disassociated this because you saw it is aqueous? A lot of you did. A very, very common mistake. But why would you not disassociate this? Because this is a weak acid. Weak acid do not disassociate completely. Therefore, this is going to stay as H3PO4. How many of you wrote this magnesium as Mg plus 2? Not going to write that. That is just going to stay as Mg. One thing, because it is a solid and it's a metal. It is not in a compound. So this is going to stay as this. Now, what is going to happen to this one? This is an ionic compound and it is aqueous. This is the one that you're going to disassociate and you will get 3Mg2 plus 2PO4 3 minus. So you need to know the charges. You need to know your polyatomic ions correctly. Again, you are not going to disassociate that because it's a gas. Right? So this is going to stay as hydrogen. Now, do I have any spectator ions in this? This is your complete ionic equation and this is also your net ionic equation over here. So what did we understand? What is important? That you need to know your strong acids. Everybody write this down. There are 6 strong acids. The acids in that 17 group, hydrofluoric acid is not a strong acid. Hydrochloric acid, hydrobromic acid and hydroiodic acid. And then with your polyatomic ion, you have nitric acid, sulfuric acid and perchloric acid. Perchloric acid is HClO4. These are your 6 strong acids. Anything other than these acids is considered a weak acid. So you need to memorize these. What that means is if any of this acid is there, you're going to dissociate it into the H plus ions and the other ion. Okay, and just I wanted to point out one more thing that I see. So did we all understand this is what is a big mistake? A lot of you disassociate weak acid. That's a problem. And then many of you, when you have a polyatomic ion, you disassociate polyatomic ion into P3 minus and O minus 2. No, no, no. You do not disassociate the polyatomic ions. Now in terms of the strong bases, all alkali, so what is a base? When it is bonded to a OH minus ions, right? So for our course, we are only going to consider alkali as our strong bases. There are exceptions where the strontium below that are strong, the other ones are not, but you do not have to worry about. We are going to look at them later on with the lens of KSP values, and then we are going to decide, or the KB values for them. Okay, so alkali compounds. Now let's say if I take an alkali metal rubidium and I drop it in water, what's going to happen? Boom! Right? Hydrogen gas. Right? And what else? Rubidium hydroxide. Many students give this as oxide. It is not an oxide that is formed. It is a hydroxide that is formed. And bond formation is a exothermic process. Bond breaking is a endothermic. You have to put in energy to break something, right? So bond formation is an exothermic reaction. So when this new bond is formed, it produces a lot of energy, and what that energy does? It lights up that hydrogen gas. So you get that flame because of the presence of this hydrogen gas, not because of this. And why? Because this is a highly exothermic reaction and it is producing heat, and this heat is being used to react with the hydrogen gas. So to summarize a net ionic equation, what are some of the things that you are going to disassociate? Ionic compounds only when they are aqueous. If ionic compound is solid, will you disassociate it? No. If you have a molecular compound. Now what is a molecular compound? Molecular compound is when a compound is between a non-metal plus a non-metal or any hydrocarbon, that is your carbon-hydrogen compound. Any of these compounds are your molecular compounds. You're not going to disassociate them. What else you're not going to disassociate? Anything that is a solid, liquid, or a gas. Okay? You do not disassociate those. You do not disassociate this. You disassociate the ionic compounds. What else do you not disassociate? If it is a weak acid or a weak base, you do not disassociate them. But if it is a strong acid or a strong base, yes, you are going to disassociate them into ions. Good? So, did I miss anything else? So, if you will remember these rules, you will never make a mistake. All right?
All right, so let's dive into net ionic equations. So these are some vocab words that I'm sure you all are already familiar with. Now we are going to focus on understanding our net ionic equation, what the difference between a molecular, ionic, and a net ionic equation is, spectator ions, electrolytes, strong acid, and strong base. So electrolytes is a word that is used when something can ionize 100%. And something that does not form ion is called a weak electrolyte. And something that does not dissociate at all is called a non-electrolyte, right? So if you look at molecular compounds, water is a non-electrolyte because it does not form ions. If I'll take methane gas, any carbon-hydrogen compounds or organic compounds, they do not form ions. Now, weak electrolytes are basically our weak bases and weak acids, right? Strong are our strong acids and strong bases, and all are ionic compounds, if they are aqueous. They are considered as your strong electrolyte. So if you look at this, this is your molecular equation where you have just written, you have not disassociated anything, you have written correct formula, and you have balanced the equation. Now, this is the ionic equation where you have disassociated everything into ions. You have to be careful because there is a 2 over here. Therefore, you have this 2Cl minus. Also, if you will notice that this one is solid, because it is solid, we do not disassociate solid in an ionic equation. It stays bonded together. So we never dissociate solid, liquids, and gases also. So this is just kind of showing you what is happening. If I'm taking this in the water, it is together, but when we add, the water is pulling it out. And understanding if you have 3 NaCl, you're going to have 3 sodium ion and 3 chlorine ion. You should be able to make sure you understand to put the correct number of ions based on the coefficient that is given to you. And if you look at this, water has not been converted into ions because it is a molecular compound. Now, if I look at this equation, this is your molecular equation. Now, if I add this equation, if I add the salts in water, when you're adding them, they are still bonded together, but as they dissolve in the water, as you can see, they are going to start changing into ions. Now, when they dissolve, eventually AgCl is going to start precipitating. Why this is not precipitating, but this is precipitating, later on when we will talk about the concept of KSP, we will look at that. Okay, but you understand that based on the solubility rule, all halides are soluble except if they are with silver, lead, and mercury. They are going to form a precipitate. And that is your precipitate. And precipitate always has a solid phase. So that was just shown with one molecule, but when I'm adding a spoonful, I'm going to have a lot of those and I'm going to have a lot more precipitate. If I'm getting a very small amount of precipitate, that means the concentration of these ions in the solution was very less. And now when I'm writing this, again, this is your ionic equation. To emphasize again, this is solid. As a result, this was not disassociated. Everything that was aqueous is disassociated. Another important thing I want to point out here is when you have a polyatomic ion, you do not disassociate the polyatomic ion into those elements. That is a complete no. And when you cancel these spectator ions, you end up getting your net ionic equation. So this is your net ionic equation. Now you can go directly from a molecular equation to a net ionic equation. To know your solubility rule, that will help you understand which is going to be precipitate. Poorly soluble salts do not ionize. That means you are not going to break them. So if it is a weak base or a weak acid, you are not going to disassociate them, even though the phase of an acid or a base is aqueous. So be very careful. Just because something is aqueous does not mean it is going to form an ion. So break down the molecules into ions. If they are molecular compounds, you do not. Make sure you're writing the correct charges. You're using the coefficient to balance the count of them, and do not break the polyatomic ions. And you will cancel the spectator ions. That is the way to write down your net ionic equation. Hope you guys all feel more comfortable with this. Right, so just here is one more example as you look at it. You can again here see this is solid. We are not disassociating the polyatomic ion. This is solid, and as a result, this is how you write down your net ionic equation. I'm positive you guys are rocking it. Do not ionize if anything is in a solid, liquid, or a gas phase. Aqueous phase, not everything ionizes. All ionic compounds in an aqueous phase will ionize, but a weak base and a weak acid will not ionize. Okay. Gases, solids, liquid do not ionize. I'm emphasizing this many times, so hopefully you will remember and not make this mistake. Think about the solubility rule. Ask yourself, is it a strong acid or a strong base? So this should be your thought process as you work on working your way up to the net ionic equation. So the solubility rules that I would recommend that you should know is for the polyatomic ion ammonium and nitrates and acetates also, C2H3O2. These are the polyatomic ions that you should remember that they are always soluble. Okay. Then the other thing is that you should know that when you have any of these cations, they are insoluble. All the other ones, we know most of the carbonate compounds are insoluble, phosphates are insoluble, hydroxides are insoluble. But if they are, so these ones you don't have to worry about as much, but you should definitely know that 1A is your alkali metals, right? So alkali metal doesn't matter whatever the polyatomic ion can be. If you have an alkali metal, any of those lithium, sodium, potassium, rubidium, cesium, those compounds will always be soluble, and as a result, they will form. So just to summarize everything we did, if it is a solution conducts, that means there are electrolytes and there are some ions present. You are going to look at anything that changes into ions is a strong electrolyte that they completely disassociates, and it will conduct electricity when you're going to put an electric bulb in it. So in terms of conductivity, molecular compounds are ionic. We should understand that molecular compounds are non-electrolytes, so they are not going to conduct, while ionic compounds will. Weak electrolytes will conduct, but it would be a much dimmer light, while if you have, if you're going to have a strong electrolyte, that is all ionic compounds that are aqueous, strong acids, strong bases, they are going to conduct a lot more electricity, right? So another example, so you have an ionic equation over here. If you look at this ionic equation, you should be able to identify the spectator ions and be able to write down the net ionic equations after you cancel them. So the thought process would be always, when you're looking at a compound, ask yourself, is it an ionic compound or a molecular compound? Then if it's a molecular compound, ask, is it an acid or a weak base? If it is a strong acid, that means it's going to form ions. If it is a weak base or a weak acid, it is a weak electrolyte, correct? And it is not going to change into ions. So you're not going to disassociate a weak acid or a weak base or a molecular compound. And most molecular compounds are non-electrolytes and they do not dissociate at all. While our weak acid and weak bases are weak electrolytes. They are not non-electrolytes, right? That is important because later on when we will do our acid-base unit, we'll get in more details with that. Thank you very much. Hope you're feeling very comfortable with writing net ionic equations. If you have any questions, don't hesitate to ask any questions in class. Bye for now. Have a great day.